let's just kind of summarize things by looking at the function that we analyzed earlier. R of t is a cosine pi t I plus b sine of pi t j. We can construct the graph in the xy plane. Now, we could just do this with a two-dimensional graph in x and y, but we want to embed this graph into 3 dimensions and relate it to the function we just analyzed. So to make this sketch, we make our square, our rectangle in general. This is a circle, so we're going to be able to put it inside of a square with sides of length 2a. Not going to go into the details of how we determine that. That should be pretty well understood by now. Curve has to be tangent to these lines. So it looks something like this. That's not perfect, but you get the idea. We're moving around a circle of radius a. And we do one cycle every 2 units of t, because of course when t changes by 2, pi t changes by 2 pi, and that corresponds to a complete circuit around the circle. This one had a very simple radius of curvature. Radius of curvature is just a, which is the radius of the circle. Curvature is 1 over a, reciprocal of the radius. Now, we consider the function another r of t function, and I probably shouldn't use the same symbol to denote both of these functions, but I'm going to use a different color. And this is going to be a cosine of pi t I plus b sine of pi t j plus rt squared k. And I want to sketch the behavior of this surface. Now let's first of all note that if we have a t squared function, okay, and if we just graph t squared versus t, our graph is going to look like this. It's going to be parabolic in shape. Now what we're doing essentially is we're taking this parabolic graph and wrapping it around a cylinder above this circle. And you'll see how that works in a minute. When t equals 0, t squared k is 0. So t equals 0, here we are, right on this circle. Let's look at t. Okay, the I and j components are going to keep going around this circle at a constant rate. Every 2 time units, every 2 units of t, we're going to go all the way around the circle. Now if this is our t equals 0 point, then we're going to be around here in 1/4 of a cycle, which is 1/4 of 2 units, which is half a unit. So at t equals 1/2, we would be here on the circle. Now at t equals 0, our t squared k was 0. That put us right on the circle. At t equals 1/2, t squared is 1/4. So that our k component, we're going to have to come up what we're going to call 1/4 of a unit here. So let's just put our point here. 1/4 of a unit above the circle. At t equals 1, here's where we are in the circle, but we're going to have to come up 1 unit, 4 times as far as we did here. So we're up 1 unit high. At t equals 3/2, we're here on the circle, and we're going to have to come up 3/2 squared, which is 9/4, 2 1/4. If this is 1 unit, 2 1/4 units is well, maybe about this high, probably even a little higher, but let's not worry too much about precision in the graphing. And then where are we? At t equals 2, we're back here again, but now our k is going to be 2 squared, which is 4, so we're going to be 4 times as high as we were here. That's going to bring us up, way up to about here. Now, how did we get from here to here to here? We followed a curve. Every point of that curve lies above a point of the circle in the xy plane because the I and j components aren't changing. That means our x and y coordinates are going to go right around the circle, and they're going to continue to go right around the circle. Our t squared k is going to increase, and it's going to increase faster and faster because of the way t squared behaves with respect to t. So our curve is going to go from this point to this point to this point to this point and this point. That's a little tricky to draw, especially when we get to the point where we have to turn around over here. But let's just do our best, and let's see if we can. Don't like the way that's coming out, but let's just continue. And we're going to come around here, and we're going to come to here, and at some point we're going to come over our line of sight, and we're going to be coming up like this. Now, this curve lies above this circle, so I'm going to draw little projection lines down to the circle to indicate our path along the curve, and it starts to look like a cylinder on which we've traced a curve. So we keep coming around like so. Now, when we get around here, let's see, we're going to be above this point, and then I guess actually we're going to come out somewhere around here, so this thing probably does some kind of little curlicue and keeps on going up. I'm not going to draw the vertical segments back here because they'll be hidden by this, but this should give us, and actually we're coming up here, should give us some picture of the path that we follow if we do this curve. Another way to visualize it is take an actual cylinder. Now, a cylinder doesn't have quite the diameter of this one, but let's just say we start here, and this is going to correspond to our xy plane. Now, we're going to draw a curve here, and as we rotate this cylinder, we're going to come up faster and faster, wrapping this t squared graph around the cylinder. Okay, it's kind of hard to keep this steady, and let's see, we're nowhere near being all the way around, but we can see how that curve could rise and how this could be a depiction of that sort of a curve. Consistent with our analysis, the curve stays close to the curve in the xy plane, to the circle in the xy plane at first, so the curvature is going to be very close to the curvature of that circle, 1 over a. As we allow t to increase, okay, on our first cycle alone we've come up 4 units. If we go to a second cycle, t is going to go from 2 to 4. Our k component is going to go from 4 to 16. This thing is going to rise more and more rapidly, and it's going to become almost straight. The curvature is going to approach 0. So we go from curvature 1 over a here to curvature 0 as we allow t to increase. And it won't take too many cycles before the curvature is going to be pretty close to 0.